Thank you to the organizing committee for giving me this opportunity to show my research work. I'm pursuing a PhD in cyberspace security at the Information Engineering University from China. Today, the title of my report is an adaptively secure NIPE scheme based on DCR assumption. My presentation will unfold from the following 4 points. 5 points: introduction, preliminaries, our scheme, security, homomorphism. First one, introduction. The traditional public key term can only achieve one-to-one scale communication, which is not conducive to ciphertext sharing. Fine-grained asset control of ciphertext is usually required in many engineering applications, such as cloud computing. Non-zero inner product encryption provides fine-grained asset control to private data. But the exciting NIPE scheme are mainly constructed in bilinear group and lattice without homomorphism. To meet the need of users to control the private data in the cloud computing environment and the direct processing of ciphertext by the cloud server, this paper proposes the non-zero inner product encryption scheme based on the DCR assumption. As shown in figure, the goal of the encryptor Alice, Bob can direct concretely if the attribute W not belong to the set omega. The non-zero inner product encryption scheme can be used for this purpose, and the specific description as follows. In the encryption, Alice constructs a polynomial phi according to the above set omega. Then embeds the policy vector A to the ciphertext. In the key generation, Bob sends his attribute vector W to the key generation center. The key generation center generates the secret key and sends it to Bob. In the decryption, Bob downloads the ciphertext C from the cloud server to the local machine, and he can decrypt it correctly. If the inner product of A and W is not zero, through the above scheme, Alice realizes the encryption and asset control of the message at the same time. The homomorphic encryption allows anyone to directly process the ciphertext without knowing the plain text, and the effect is equivalent to operating on the plain text first and then encrypting the result. Homomorphic encryption can be widely used in secret booking, bidding, and so on. According to the type of homomorphic mapping, homomorphic encryption schemes can be divided into additive homomorphism and multiplicative homomorphism. For example, RSA and EGML encryption belong to multiplicative homomorphism, while Paler encryption belong to additive homomorphism. To illustrate the practical application of non-zero inner product encryption with additive homomorphism. This figure shows a non-zero inverse product encryption for carrying of average salary. In the encryption, I use the NIPE scheme with additive homomorphism to encrypt the everyone's salary. The first M, the second M, and the 12th M in a department and obtain the ciphertext screens, which is embedded with the same police vector. Then upload the ciphertext screens to the closed server. In the key generation, Bob sends his attribute W to the key generation center. The key generation center generates a secret key and sends it to Bob serially. In the query phase, Bob wants to know the average salary in this department. So he sends a request to the closed server to query the average salary. In the operation phase, the code server calculates it and sends it to Bob. In the decryption phase, Bob can get the ABE if his attribute vector and the police vector in ciphertext meets the conditions. In terms of design ideas, based on the exciting design technology of inner product function encryption compared with Taylor encryption, we propose a non-zero alpha product encryption scheme supporting adaptive homomorphism. And it has the following features. First, it supports adaptive homomorphic encryption. Secondly, it is adaptively secure. Thirdly, it supports faster decryption. The second one, preliminaries. In the setup phase, randomly choose two large prime numbers P and Q of equal length such that output the public key and the secret key. In the encryption phase, input the plain text and randomly set R. Output the ciphertext as follows. In the decryption phase, input the ciphertext public key and the secret key, and then output the plain text as follows. As DCR assumption, given n is equal to PQ, where PQ are two large prime numbers. Define the DCR assumption as follows. For any probability polynomial time adversary, the advantage of distinguishing the following two descriptions is negligible. For example, the one DCR is this. The next one, formal definition. In the setup phase, it inputs the security parameters lambda and n, outputs the master public key MPK and the master security MSK. In the encryption phase, it inputs the plain text M and vector Y, output the ciphertext. In the key generation phase, it inputs a attribute vector X, output the secret key SK. In the decryption phase, it inputs X and SK and Y and C1. Output the plain text if the inner product of X and Y is not 0. Adaptive security model. In the setup phase, challenger B runs algorithm setup, then sends MPK to adversary A. In the query phase 1, adversary A adapted to the attribute vector X for secret key query. Challenger B runs the key generation and required to A. In the challenge phase, adversary A submits 2 equivalence messages, and the challenge vector Y to challenger B. Any challenge vector Y and X satisfy this. Then challenger B samples B, runs algorithm encryption and returns ciphertext of MB to adversary A. In the query phase 2, the adversary may do more security queries. The specific steps are as query phase 1, guess. Adversary also guess B about it, and of adversary A with this game if this. Define advantage of adversary A is it. The scheme is adaptively secure if it is negligible function for any probability polynomial time adversary A. A second part. In the setup phase, the master public key is it. The master secret key is the vector S. In the encryption phase, the ciphertext C is this. We can say it is different from pillar encryption, and our scheme is there is a Y. In the key generation phase, the secret key SK is the inner product of the vector S and X. Then the decryption phase. First of all, compute the C as follows. 2. Compute the Z is it. 3. Output the plain text. Example of scheme. Let the number of attributes in is 2. The security parameters lambda is 2, and p lambda is equal to lambda. Then the prime number of equivalence P is 12 and Q is this. And then N choose G is 3. S1 and S2 is 2 and 3. Then H1 and H2 is this. Out of the MPK and MSK. In the K generation phase, that attributes vector X. Compute and output the security key SK is this. In the encryption phase, let M is 5. The vector Y is 1 and 2. Choose R and output the ciphertext as follows. In the decryption phase, firstly, compute this and this. Secondly, compute each and it. Thirdly, compute Z and the inner product of the vector X and Y is 6. Finally, output the plaintext M is 5. The security. Our security proof relies on a series of games which are declared below. Table shows some parameters in these 4 games. Game 0. The original set term generates a secret key and the ciphertext. Game 1, same as game 0, but the range of SI is changed. Specifically, the challenger B reduces the upper bound of SI, such as this. Note, the upper bound of the value of SI is reduced in game 1, and the upper bound of the value is restored to this by a special parameter second middle in the program game 3. This step is to prepare to find the equivalent parameters in game 3. Game 2, compared to game 1, modified the challenge ciphertext state specifically. The challenge computes this. The modification is to connect the archaic team with 1 DCR assumption. Game 3, modify the first item of the challenge ciphertext as it. Now the game 3 is designed to make a ciphertext of M and 1 set of parameters from the algebraic encryption. Equivalent to the ciphertext of M1 and another set of parameters. And the adversary cannot distinguish between these 2 sets of parameters. So the adversary's archaic advantage is almost 0. The scenario 4, based on the 1 DCR assumption, the non-zero inner product encryption scheme based on Taylor encryption proposed in this paper is adaptively secure. It's our idea. 5. Homomorphism. The following shows that the scheme in this paper has adaptively homomorphism, where M1, M2, and MK represent the K plaintext and M is smaller than N. We can explain it. Example. That the number of attributes L is 2. The security parameters lambda is 2, and P lambda is lambda. We can output the MPK and MSK as above. In the K generation phase, that attribute spectra as above, and compute output secret K as K. Now, in the encryption phase, it's not the same as above. That M1 and M2 is 4 and 5. The vector Y is 1 and 2. 1 and 2. Choose R1 and R2 is 2 and 3, and output these two ciphertexts as follows. Query. User B sends a query request for M to the cloud server. In the compute phase, the code server calculates the new ciphertext as follows and send it to B. In the decryption phase, user B first compute this. The study compute Z is 34, and the inner product of the vector X and Y is 6. Finally, out of the plaintext M is 9. We can deny the sum of M1 and M2 is 9. Thank you. Thanks for your listening.